Welcome to the Explainer. So if you've ever looked up and felt like our progress into the cosmos is just dragging its feet, or maybe costing way too much, you are going to absolutely love what we're unpacking today. We are diving into some truly brilliant, borderline sci-fi engineering concepts. Our mission? To explore exactly how humanity plans to conquer gravity and blow the solar system wide open, without relying solely on traditional rockets.
To really understand why we so desperately need alternatives, we just have to look at the current price tag. $25,000. Let that sink in for a second. That is how much it can cost to launch a single kilogram into low Earth orbit right now, using traditional rockets. Even on the absolute lowest end, we're talking around $2,500 per kilo. It creates this massive financial bottleneck that practically halts humanity-altering space endeavors right in their tracks.
And the reason for this insane cost? It all comes down to our main villain for today, the tyrannical rocket equation. This fundamental rule of physics dictates that lifting mass requires exponentially more fuel. Why? Because, well, you have to burn fuel just to lift the unburned fuel. It is a vicious, heavy cycle that leaves almost zero room for your actual payload. But if we can provide even a little bit of that orbital velocity by other means, we can finally break free from this equation.
Here is our roadmap for today. We're going to start with the core problem with rockets. Take a look at megastructures, jump into projectile launchers, explore hybrid systems, and finally, look at a future solar system entirely unlocked by these innovations.
All right, Section 1, the problem with rockets, and exactly why we need alternatives.
The math here is just staggering. When you contrast the thousands of dollars required by rockets against theoretical concepts, the difference is night and day. Take the Star Tram. That could slash costs down to a mere $43 per kilogram. Or the launch loop. That could potentially drive costs down to just $3 a kilo, while lofting millions of tons every single year. If we can actually build these things, the economics of space travel change overnight. We're talking unlimited clean energy from space-based solar power, and yes, totally affordable space tourism.
Moving right along to Section 2, megastructures, reaching for orbit.
When we think about building our way up to orbit, there's this really fascinating architectural tug-of-war. First, you have static compression towers, right? Built from the ground up. The big problem there is that literally no known material can support its own massive crushing weight at that height without buckling. But what if we flip the physics upside down? Enter tensile structures like the space elevator. You anchor a cable to Earth and extend it way past geosynchronous orbit. The Earth's rotation creates centrifugal force at the very top, keeping the entire tether perfectly taut. It's exactly like a string you're spinning with a rock attached to the end. Now, doing this on Earth is incredibly tough because our heavy gravity demands phenomenally strong materials like carbon nanotubes, which, to be fair, are still pretty theoretical at that massive scale. But here is the exciting part. Because of the lower gravity on the Moon or Mars, we could actually build a space elevator there today using commercially available materials. We're talking Kevlar. Yes, the exact same stuff used in bulletproof vests could literally build our highway to orbit on Mars. How cool is that?
So, how do we get around the material limits here on Earth? Well, engineers came up with dynamic structures. Instead of standard solid supports, these use constant active motion to hold themselves up. The space fountain, for example, shoots massive pellets upward, using the kinetic force of redirecting them to hold a tower aloft. The orbital ring envisions a massive artificial ring spinning around the planet at superorbital speeds. And the launch loop, that is a staggering 2,000-kilometer-long maglev belt that maintains an 80-kilometer-high track entirely through sheer kinetic energy. It sounds like literal magic, but it is just brilliant physics.
I know, it all sounds impossible, but the math does check out. As the early space pioneer Konstantin Tsiolkovsky so beautifully put it, the Earth is the cradle of humanity, but mankind cannot stay in the cradle forever. Overcoming these monumental engineering hurdles isn't just a sci-fi dream, it's our inevitable next step.
All right, Section 3, projectiles. Literally shooting things into space.
Stepping away from giant megastructures, projectile launchers take a much more brute force approach. The whole genius behind electrical systems like Star Tram is using magnetic levitation. Instead of putting incredibly heavy engines and fuel onto the spacecraft, you just build the engine into the ground. Star Tram proposes accelerating cargo inside an evacuated tube straight up the side of a mountain using maglev. It would launch vehicles at 10 to 20 Gs, basically hurling cargo into orbit for around $40 a kilogram. And the best part? It doesn't carry a single drop of liquid propellant during the launch phase.
Then you've got chemical projectile systems, like the RAM accelerator. This one is super cool. Unlike a traditional space gun that relies on pressure pushing a projectile from behind, the ram accelerator acts exactly like a jet engine inside a gun barrel. You fill a long tube with combustible gases, right? Then a projectile shaped like a ramjet core is fired into the tube at supersonic speeds. As it travels, it literally swallows and burns those pre-placed gases, accelerating down the tube via jet propulsion. It is a wildly clever way to hit hypervelocity.
And for mechanical systems, we have things like the slingatron. I know, wild name, but think of it exactly like stirring a beverage in a glass. You move the glass in small circles, which causes the liquid inside to spin faster and faster, without actually spinning the glass itself. In a slingatron, a rigid track gyrates in small circles at a constant speed. It continuously pushes the projectile outward, faster and faster, until it hits extreme hypervelocities and is just flung into the atmosphere.
Now, if you're sitting there thinking this is all just chalkboard math, think again. Giving us an amazing dose of real-world reality, the aerospace company Spacelaunch is actually doing this today. They've already built a giant, vacuum-sealed centrifuge that aggressively hurls payloads towards space at speeds up to 4,700 miles per hour. It totally proves that mechanical kinetic launch systems are a very real, near-term possibility.
Which brings us to Section 4, hybrid systems, the practical middle. If sky-high megastructures or firing giant space guns into the void feel a little too intense, hybrid systems offer a really pragmatic middle ground. By using high-altitude balloons for things like rockoons, which yes, literally means rocket balloons, or using carrier aircraft and magnetic ground sleds, we can bypass the thickest, hardest part of the atmosphere to get our initial momentum. Remember the rocket equation from earlier? By providing just a fraction of the thrust through these alternate methods, we exponentially reduce the weight of the fuel required for that final rocket stage. It is a massive masterclass in efficiency.
Finally, Section 5, opening the solar system.
The ultimate payoff here is absolutely staggering. Look at these numbers. Traditional expendable rockets measure their annual payload capacity in the hundreds of tons. But if we successfully develop something like a star-tram system, that leaps to 150,000 tons. The launch loop, 6 million tons per year. By finally escaping the rocket equation, we shift from lifting mere hundreds of tons to millions. And that is what makes massive space colonization and off-world industry a true fiscal reality.
The math is proven, the physics are completely sound, but the engineering is undeniably monumental. Whether it ends up being spinning tethers hanging from the sky, giant magnetic railguns built into the sides of mountains, or hybrid maglev sleds, the alternatives are out there, waiting to be built. So which of these concepts do you think will truly open up the solar system for us all? Thanks for joining me on this explainer. Keep looking up, and I'll catch you in the next one.